Okay, guys, today we're going to be talking about multiplying and dividing radical expressions in this video, and then a later video we're going to be doing adding and subtracting radical expressions. So much of this is review, so we're going to tie this into what we learned the other day. Um, so what we know already is when we're multiplying, let's say like a monomial times a monomial, we would multiply coefficient with coefficient and variable with variable. Okay, we're going to operate in the same manner here when we're dealing with irrational values and irrational values. So rational values, any number on the outside can multiply with a number on the outside, another rational value. But irrationals, so anything under the radical, can multiply by each other as long as the index is the same. So we have a square root and a square root, so we can multiply the contents of what's underneath this radicand with this radicand. So 3 times 27 is 81. P to the third times P to the first is P to the fourth, and Q to the third just stays there. Now we can start breaking this up. Square root of 81 we can take, it's 9. Square root of P to the fourth we can take, it's P squared. We do not need absolute values since it's raised to the second power. And the square root of Q squared, we have to break up Q to the third into Q squared and Q to the first. We take the square root of Q to the second, it's going to be absolute Q, and this Q to the first will stay underneath the radical, because the degree of 1 is less than the index of 2. Okay, now that same approach is going to carry over regardless of the index. Now we warmed up with something you've seen before, which is square root radicals, and now we're just going to change our line of thinking when we get into cube roots. So like I said before, the 7 out front is rational, while the 9n squared is irrational since it's under the radical. The 4 outside is rational, but the 24n underneath the cube root radical is irrational. So the rational times rational, 7 times 24 is going to give me a coefficient of the radical of 28. And then the 9 times 24 can give me 216. N to the second times n to the first is going to give me n cubed. Now, we'll break things up into perfect cubes. So the cube root of 216 is going to be 6. And the cube root of n to the third is n. There is no need for absolute values when taking an odd root. Like we said before, the cube root of 8 is only positive 2, and the cube root of negative 8 is only negative 2. So now we can simplify here. 6 times 28 is 168, and 168n is simplified. Now, one of the things that I encourage you to look for, if you start to recognize things that are on our table of powers to memorize, like 9 is really 3 to the second power. In order to get it to a perfect cube, you need one more factor of 3. So that's why I would consider breaking up the 24 into 3 and 8. The 3 joins with the 9, and now you have 27, which is a perfect cube root, and we would take it and get 3. And 8 by itself is also a perfect cube, and it would get you 2. So 2 times 3 would give us the 6 that we would get in this step here. So try to look to see if you can break things up rather than multiplying them all together first. Okay, now things we need to consider. A radical expression is considered simplified when the following conditions are met. So the first is the radicand contains no factors other than 1 that are the perfect nth power of either an integer, a variable, or a polynomial. Okay, it's going to be a rarity that is polynomials, but we'll do those with square roots. But integers and variables, we're going to be taking the third root, fourth root, fifth root, sixth root, you name it. So no perfect nth roots other than 1 underneath the radical sign. Also, the radical can contain no fraction. So if we have a fraction, we're going to break it up. And no radical can appear in the denominator, and I'll explain a little bit more why in the next slide. Okay, so if I had the square root of 5/3, right, we have a fraction underneath the radical, so the first thing we would do is break it up into the square root of the numerator over the square root of the denominator. And so I said I'd explain here, it's very easy to take a value and separate it into 3 equal groups, okay? So breaking things up into equal groups as an integer, very simple. The square root of 3 is like 1.7 something, okay? So this goes on forever. It's irrational. It's very difficult to break things up into square root of 3 equal groups. So what we're going to always try to do is rationalize the denominator. Now, I don't want to change its value. So we're going to multiply by something that's equivalent to 1. In this case, root 3 over root 3. We did this because root 3 times root 3 will get us to root 9, which is a perfect square root, and we can take and we'll get 3 in the denominator. There's no perfect square factors other than 1 in your numerator, so the top is fine. There's no fractions underneath the radical, and the denominator has a rational value, no radicals there. So this is now simplest radical form. Now that same idea has to be changed slightly as we go from index to index. So the next example is dealing with cube roots. So if I had the cube root of 5/3, the first thing I would do is there's a fraction underneath the radical, so we'll break it up, and we'll do the cube root of 5 over the cube root of 3. Although now we can't just multiply by the cube root of 3, we have to multiply by a value that will get us to a perfect cube in our denominator. So 3 times 9 would get me to 27, which is our next or our smallest perfect cube root that we can get to. So we're going to multiply top and bottom by root 9, cube root of 9 over cube root of 9. That's going to give me cube root of 45 in the numerator. And once again, cube root of 27 in the denominator. Cube root of 27 we can take, it's 3. And so now we'll have the cube root of 45 over 3. There's no perfect cube factors other than 1. Okay, there no fractions underneath the radical sign and no radicals in the denominator, so you're in simplest radical form. Once again, we'll look at the same problem, but change the index. Now it's the 4th root of 5 over 3. There's a fraction underneath the radical, so we'll break it up. Do the 4th root of 5 over the 4th root of 3. Okay, now I need to get it to the next perfect fourth, which in this case is 3 to the 4th, or 81. So we're going to multiply really by 3 to the 3rd over 3 to the 3rd. 3 to the 1st times 3 to the 3rd would give us 3 to the 4th. And that's going to be the 4th root of 27. Okay? So anything over itself is 1, so we're not changing the value, just the way it looks. 5 times 27 is going to give me the 4th root of 135 in the numerator. 3 times 27 is going to give me the 4th root of 81. 4th root of 81 we can take, it's 3. And now we have the 4th root of 135 over 3. There's no perfect 4th root factors other than 1 in your numerator. There's no fractions underneath the radical, and there's no radicals in your denominator, so you're in simplest radical form. Okay, now let's talk about foiling, and I apologize I had to do all this out. I can't really write in the Jamboard from home. So if we had the binomial 2 root x, 2 square root of 6 minus 3 square root 2, parentheses, and then 3 plus root 2, we're going to FOIL this. So first times first, it would be rational times rational. 2 times 3 is 6, so 6 root 6 would be our first product. Outside times outside, we've got 2 root 6 times root 2. The rational times the rational, we multiply here, so we get 2 root 12 as our next term. And we can simplify 2 root 12. We can break it up into root 4 and root 3. Square root of 4 is 2. That becomes rational and can multiply with the 2 already on the outside. And that's going to simplify to 4 root 3. Now, inside times inside, rational times rational. So negative 3 times 3 is negative 9. So it's going to be negative 9 root 2. And then last times last is negative 3 root 2 times root 2. Root 2 times root 2, those irrational values can multiply, so we get negative 3 root 4. Square root of 4 you can take would be 2. That becomes rational. The 2 multiplies with the other rational value, negative 3, and we get negative 6. Now in this case, this is as simplified as we can get. We have 3 unlike radicals, so if they're not the same, they cannot be combined together. Now in the next example, I chose this specifically because these are what are referred to as conjugate values. The same values with one sign difference. So here I have 3 root 5. I have a 3 root 5. They're both positive. Here I have a 4. There I have a 4. One's positive, one's negative. So the same values, but one sign difference. When we FOIL this, we're going to get a difference of 2 squares effect. So first times first, rational times rational. So 3 times 3 gives us the 9. Root 5 times root 5 gives us root 25. Well, the square root of 25 we can take. It's 5. 5 times 9 gives us 45. Now, outside times outside, rational times rational. 3 times negative 4 is going to be negative 12 root 5. Inside times inside. 3 times the 4 is 12. Here's a positive 12 root 5. Anything plus its opposite cancels. So the only values that are going to contain the radical get canceled. Now, last times last, 4 times negative 4 is going to give me negative 16. And when you multiply anything by its conjugate, we're always going to get a rational value. Okay? This is very important when we get into the last phase of rationalizing a denominator. Okay, so in a case like this, pretend this was my problem right here. I have 2 over root 5 plus 3. I need to get this into simplest radical form, but there's a radical right here in my denominator, and it's only in one term. So in this case, what we're going to do is we're going to multiply by something over itself. This is equivalent to 1. Anything over itself is equivalent to 1, but it's the conjugate. So when we multiply top and bottom by the conjugate, the denominator is going to become rationalized. Now, if you'll notice, I didn't distribute initially the 2 into the root 5 minus 3. I wait until I'm done simplifying the denominator, and here I get root 5 times root 5 is 25, which would just be 5. The outside inside radicals will cancel, and last times last will give me negative 9. 5 minus 9 is negative 4. It's at this point, that's why I didn't distribute the common factor of 2, because I can now cross-reduce, or just reduce. So the 2 and the 4, or 2 and the negative 4, will reduce to 1 and negative 2. Now remember, we don't like to keep negatives in the denominator, so we're just going to slide that negative up to the top and distribute. So root 5 minus 3 is going to become negative 5 plus 3 over a positive 2, and then we'd be simplified and rationalized. There's no perfect square factors other than 1 under the radical. There's no fractions under the radical, and no radicals in the denominator.